Thank you, Dr. Dharma. Good afternoon, ladies and gentlemen. I'm Velu Subramani. I'm presenting this paper instead of my colleague, Dr. Santosh Gangwal, who is currently on travel. First of all, I would like to apologize for a small change in the title of my presentation because while submitting the abstract, we were planning to present recent data on evaluation of novel iron-based pressure-proof catalyst continuously for 500 hours of operation. But however, because of the serious negotiations going on with the commercial client, so we are not able to present those data. However, I will be presenting part of the data and the summary of the 500-hour long-term operation. And I have my son, director. If you have any question, specific question on this presentation, we will be happy to answer. So what I'm going to do is in the first few minutes, I would like to briefly highlight the importance of development of iron-based pressure-proof catalyst, the objective of our work, then the history of iron-based, summary of iron-based pressure-proof catalyst development at RTI, where I will be comparing the data obtained from 3 different reactors, namely fixed bed CSTR and cylindrical column reactors. And finally, a summary of 500 hours continuous operation in the CSTR and conclusions. So, the increasing crude oil prices, crude oil and natural gas prices are attracting more, is attracting the pressure-proof synthesis reaction in recent years. Because this process can produce clean fuels from various alternative feedstock like coal, heavy residue, petroleum coke, and biomass, which are cheaper and domestically available. So it makes sense to gasify some of these solid feedstock into synthesis gas, followed by pressure-proof reaction to produce clean liquids and lubricants. But the process involves several steps, namely producing synthesis gas from various feedstock like natural gas, from natural gas either by converting into partial oxidation or steam reforming or gasification of coal or biomass to produce synthesis gas, followed by syngas cleanup to remove various contaminants like particulates, sulfur and tar, followed with low temperature pressure-proof reaction to produce high molecular weight diesel products, or low temperature pressure-proof reaction to produce gasoline range hydrocarbons. So the catalysts known for pressure-proof reactions include mainly cobalt-based or iron-based, and rarely ruthenium-based catalysts. The cobalt-based catalysts are known for suitable higher hydrogen to CO ratio. It's also known that the higher cobalt-based catalysts are known to exhibit very high selectivity towards paraffins. Also, they exhibit a higher activity and stability than iron-based catalysts, but it causes lower water gas shift activity. On the other hand, iron-based catalysts are suitable for syngas with a lower hydrogen to CO ratio, and also iron-based catalysts are lot cheaper than the cobalt-based catalysts, and it's known to exhibit high activity and low methane selectivity, and also the ability to participate in the water gas shift reaction to produce more hydrogen for pressure-proof reaction. So this slide shows the various hydrogen to CO ratio produced from the wide range of feedstocks. As you can see, wide range of feedstock like coal, naphtha produces hydrogen to CO ratio below about 1.6, where iron-based catalyst can be used. On the other hand, cobalt-based catalyst has a narrow hydrogen to CO ratio of close to 2, which can be obtained mainly from natural gas by steam reforming. Coming to the reactors, generally fixed bed micro-reactors or CST are generally used for catalytic development. But in commercial process, slurry reactors like SBCR is preferred because of the excellent heat removal and better temperature control, and also the reaction carried out in a liquid gas product medium. The ability for only catalytic addition and removal are also simple to reactor design and scale up, and also lower capital and operating costs. So the integration of gasification and pressure synthesis seems to be simple, but the challenge here is we need to have a catalyst that is highly addition resistant. Also, in addition to addition resistant, the catalyst should also have high alpha, that is the chain growth probability factor, in order to produce hydrocarbon with a very high molecular weight like C5+. So the objective of our work was to develop iron-based pressure probe catalyst with a high addition resistant, high alpha, high activity and stability, also using scalable, and then to evaluate the long-term activity in the slurry reactors, and then work with the commercial client and commercialize the technology. So RTI has been involved in developing both cobalt-based and iron-based catalysts for the past 20 years. And more than 100 different catalysts have been synthesized by spray drying and tested over 3,000 hours in various types of reactors and fixed bed CSTR and SBCR. Recently, we have developed a novel iron-based catalyst that has been scaled up to 30 lb per quantity. There are few publications in the past on the iron-based pressure probe catalyst development in our laboratory. So the recent development in the RTI on the iron-based catalyst, it has been tested extensively in different reactors, fixed bed CSTR and PCR. And it has been observed that the catalyst can produce C5+ hydrocarbons with the low selectivity for C1 to C4 hydrocarbons. So it shows very high chain growth with alpha. And the catalyst is suitable for syngas with a low CO to hydrogen ratio. We have also noticed that the catalyst can be easily separated from wax. We have characterized the catalyst using a variety of physical methods, including Jacob addition method, chemical addition by scanning electron microscopy and redox and particle size distribution, structural properties like surface area and pore size distribution, also the structural properties by XRD and mass boil and PPR, but unfortunately I'm not allowed to present these results at this moment, but I would like to briefly share the SEM pictures. The SEM pictures are being taken in order to investigate the chemical addition of the particles. This at the top, the SEM picture of the calcium catalyst. At the bottom, the same catalyst activated under different conditions, namely activated in the presence of hydrogen, activated in the presence of carbon monoxide with a lower flow rate. This catalyst activated with carbon monoxide with high flow rate, and catalyst activated in the presence of syngas. Basically, the results show that there is no significant difference in particle morphology. Actually, the catalyst, even after activation, it presents as agglomerated particles without any crack or flaws, and also the polyethylene shows smooth surfaces. So this indicates that the catalyst particles are strong and they are resistant to chemical addition. So at RTI we have capability for evaluating the catalyst by fixed bed microreactor with a 1 to 3 cc catalyst capacity, and we have experience of evaluating the catalyst continuously for 20,000 hours. And the reactor can be operated at high pressure up to 400 degrees C and 400 psi. Also, we have a CSTR 1 liter autoclave with a capacity of 10 to 50 cc catalyst. And we have experience of evaluating the catalyst for 2,500 hours. And the reactor can be operated up to 1,000 psi and 450 degrees C. We have recently installed a slurry bubble column reactor with a 1.25 inch ID and 7 feet high. This can be operated up to 1,000 psi pressure and 400 degrees C. And this has a capacity of 200 to 400 cc catalyst. Recently, we have evaluated the RTI catalyst Rentec in a slurry bubble column reactor. And we also have an analytical system capable of analyzing products online, various GC, the TCD and FID data, also GCMS for online and offline analysis, and also dedicated GC for analyzing the heavy hydrocarbons. The catalyst development activities involve synthesizing a wide range of catalysts, employing various methods, and screening the catalyst in a high pressure microreactor. The selected catalysts are synthesized, scaled out by in-house spray dryer and evaluated in the CSTR. Finally, the selected catalyst is scaled out by a commercial catalyst manufacturer and evaluated in a slurry bubble column reactor. So this is comparison of data obtained in 3 different reactors: fixed bed, CSTR, and SBCR. As you can see, the C5 selectivity is almost close to for in the case of fixed bed and slurry bubble column reactor. Although the hydrocarbon productivity was relatively low. This may be because in slurry reactors, the conversion and the selectivity are governed by the exit composition. We have also read the effect of temperature on the hydrocarbon productivity and C10 plus yield. What we noticed was as we increase the reaction temperature, the C10 yield decreases, while the CO hydrocarbon productivity increases. This data is obtained at Rentec, or continuously running the experiment in a slurry bubble column reactor for about 70 hours. So this slide shows the CO conversion and hydrocarbon productivity. As you can see, the conversion, CO conversion remained about 55%. The hydrocarbon productivity also remained about 25% during the reaction. This slide shows the methane and the CO2 selectivity over this 75 hours of run. As you can see, the selectivity for this product, CO2 and methane, has remained unchanged. This slide shows the separation of catalysts from the wax. As you can see, the top of the wax is completely free from iron. All the iron is settled down at the bottom. In order to further confirm, we have also carried out a TGA analysis. This is a TGA spectrum. As the temperature increases, as you can see that the weight loss reaches zero, indicating that there is no iron present in the wax. So, based on the Rentec continuous operation, we have a catalyst with a scale of a commercial manufacturer up to 30 lb, nearly zero attrition in 80 hours slurry bubble column reactor test at Rentec. The alpha of this catalyst has been determined in the range between 0.93 to 0.95, and it's a high chain growth catalyst. The product selectivity was about C5 productivity was about 250 kg per tan per hour with 58% selectivity, and C10 plus yield was about 200 kg per tan per hour. We also observed that the mutant selectivity remained below 2%. Finally, this is a summary of our 500 hours continuous operation in a CSTR. The experiment was performed at 375 psi, the temperature range between 240 and 275 degrees C. The space velocity of 2.19 liters per hour per gram of the catalyst. We used an inlet gas composition containing 55% carbon monoxide, 39% hydrogen, and 6% argon as internal standard. This gives us the hydrogen to CO molar ratio of 0.7. We used 150 gram of ONX fluid as the initial liquid medium. The catalyst was about 10 gram. The particle size of between 45 and 90 microns. We obtained on the steady state, the CO conversion was about 40%, which is close to the Rentec data. The C5 plus yield remained constant, about 0.15 gram carbon per gram of catalyst per hour. The C1 to C4 hydrocarbon remained below 0.02 gram of carbon per gram of catalyst per hour. During steady state operation, the amount of water produced was about 0.75 gram per hour, and organic liquid production rate was also about 0.59 gram per hour. The amount of wax produced was about 1 gram per hour. So on this, I would like to conclude that RTI has over 20 years of experience in developing both cobalt and iron-based catalysts. Recently, a novel iron-based catalyst has been developed and proven independently at least 3 different FT catalyst developers, tested in different reactors, CSTR, slurry bubble column, and fixed bed reactors. The long-term activity test demonstrated high attrition resistance and exhibits high alpha and also high activity and selectivity after the induction period. The catalyst has been produced by a commercial manufacturer to demonstrate the production scale-up, and catalysts and process are currently being commercialized. And finally, I would like to acknowledge the Department of Energy for the financial support, and Clemson University and Rentec for the catalyst test and collaboration. Thank you very much for your kind attention. I'll be happy to answer your questions. Yes.
I'm a little curious as to your statement that a slurry bubble column reactor is easy to scale up. Do you mean easy to construct or easy to predict the performance of when you said that that's easy to scale up? You want to hear what he said?
You're asking whether it's easy to scale up?
Well, I'm surprised, yes, I'm surprised to hear someone say that it's easy to scale up a slurry bubble column reactor, so I was asking for clarification of what you mean when you say that.
I think what we mean is if you go with the fixed bed to the slurry bubble column,
Yeah.
you can deal with the heat much easier in the slurry bubble column than the scale up. That's basically the
Okay.
that's the intent there. I'm not talking about the hydrodynamics. Hydrodynamics
Okay.
is pretty complex.
That's what I was
Yeah.
surprised about.
Yes, please.
Yeah, in one of the slides you show the CO2 selectivity being 30% in two different reactors and 40% in one of the reactors. Why is there such a big difference?
Probably in fixed bed. This one? Okay, CO2 selectivity is this. You have low selectivity in fixed bed, high selectivity, relatively high selectivity in CSTR and SBCR. I think in the slurry reactors, the composition of the product is governed by the exit gas composition, exit product composition. That could be a reason.
Were the experiment run at the same condition, or maybe they are?
Well, yeah, there is a range. I'm not sure whether it's statistical condition or not.
It's not identical.
Okay, this 30 and 40% is quite different in terms of productivity, ultimate productivity.
Yeah, there's a change. There's a range of temperature and pressure from this. There might be some differences in operating conditions.
Amitabh has a question. Amitabh.
You have this nice picture of the wax and catalyst separating.
Yeah.
Sort of two questions related to that. I perhaps missed this. Exactly how did you separate these? And two, after that you sort of showed the graph TGA or whatever that said there was basically no catalyst in the wax. In reality, in terms of parts per million on the top portion, how much catalyst was there?
Do you have any?
Yeah, answer. What we did, you can separate it just by heating it up because the iron particles, will settle down in the water, and we have been able to do it. When we try to measure the iron concentration in the wax, it was below the detectable level limit of the iron measurement we could do. So that's why we went to the TGA and see if we can track the microgram weight track. So we really didn't see any wax in any detectable amount of iron.
So you let the 30 to 60 micron catalyst sit in typical wax,
because the
and it
density
just separated out to zero.
Yeah, right, absolutely. That's what it is. Because the catalyst does not attract, so it does not get into real fine particles in the wax.
Okay, before Amitabh assessed the subject result, you showed your addition resistant results by comparing different activation conditions. Do you know the degree of activation in the catalyst from each activation condition?
Let me see if there is a condition of it. This is
It's very,
the data has been published few years ago.
yeah,
Okay.
this,
Yeah,
the
this-
degree of activation for each case?
I don't remember how many hours has been activated, but this information is available. It's already published.
Okay.
It's long back, so
Amitabh.
yeah, sure. This one will proceed.
You showed one of the best tests was stable at 40% conversion.
Okay.
Is that, you qualify that as a commercially viable option? You operate at 40% conversion?
I'm not sure how much is the conversion. I think the commercial scale, the productivity of C5 plus is important. But the conversion could be, I think, anywhere from 40 to 60%. I'm not sure in commercial scale what is the conversion level is expected.
In that slide, you show different ways of activating the catalyst. Is there any one preferred versus the other in terms of productivity and selectivity and activity in general? Do you prefer one, A, B, or C, or D?
Actually, this test was done in order to see the chemical addition of the catalyst. So in the presence of, when you activate in the presence of hydrogen, syngas, and CO, what happens to the catalyst particle, whether it cracks or it remains intact. Usually the catalysts are activated in the presence of carbon monoxide in order to carbonate the ion. So I think that the activation in the presence of carbon monoxide is required for commercial scale.
Usually in a commercial plant, it's difficult to have carbon monoxide.
Well, that's why we tried the syngas one. That's what I want to see if we can do the syngas itself. That was the intent there, you know. So, again, we are looking into a lot of strategies in terms of how to do it.
So, okay, thanks.
But on the other hand, it's
You mentioned that the initial particle size distribution was around like 10-40 micron. Have you done any particle size distributions?
Yeah, we have done a lot of analysis. I am not presented because of some. So I hope we have a
You
lot
don't
of
see any
data.
addition or any?
No, not significant addition.
yeah, but before saying that, I would look at the video of activation to make
I
that
can tell you in another 10-15 minutes if you want, because it's known.
Okay, we'll do that.
Okay.
Thank you very much. Do you have any more questions? Okay, thank you very much, Gary Jacobs from Center for Applied Energy Research, University of Kentucky, and his paper is on Fischer-Tropsch synthesis, investigation of the metal support interaction of cobalt-based catalysts by standard TPR and synchrotron-based TPR, same TPR techniques. It is always organized.
Do you know where the clicker is? Is this it?
No, it's-
No, it should be set. Oh, there it is. Thanks. Okay, today I'm going to talk a little bit about a novel technique where folks at Argonne National Lab have combined TPR with ZANES and XAFs. And I want to show how this is a very powerful tool for characterizing cobalt-based Fischer-Tropsch catalysts. And let me first acknowledge my coworker, Yaying Ji, my supervisor, Professor Davis, as well as our colleagues at Argonne, Donald Kronauer, Chris Marshall, and Jeremy Croft. Of course, we all know that cobalt-based Fischer-Tropsch synthesis catalysts are usually the catalyst of choice for converting natural gas-derived syngas. And there are a number of motivations for doing this recently. And I want to point out that Sasol has claimed a capable cobalt Fischer-Tropsch synthesis catalyst supported on alumina. And this catalyst has very, very high loadings. It's 33 grams of cobalt per 100 grams of alumina. So part of our motivation has been to try to prepare highly active catalysts with less cobalt. So it'll be part of the focus of this talk. We present an outline. We'll examine factors that influence the active site densities for supported cobalt catalysts and show how the support type, the loading, and presence or absence of promoters can influence the active site density. And discuss this trade-off that exists between cluster size after reduction and the extent of reduction of the cobalt clusters and how the support influences that. And then finally, we'll investigate the susceptibility of cobalt clusters to deactivation phenomena, which is exacerbated by the presence of water. Pinpointing the active site, Professor Iglesias showed this very nice plot here, which basically shows that Fischer-Tropsch synthesis over cobalt is a structurally insensitive reaction. Basically, CO conversion follows the cobalt dispersion very well over a wide range of catalysts, and that means that the turnover frequency per active site is essentially constant. We prepare catalysts by standard aqueous impregnation methods using cobalt nitrate as a precursor, and we have to use several impregnation steps due to the solubility limit of cobalt. And we add our promoters before we calcine the catalyst. First technique we use to characterize a catalyst, the reducibility, is temperature program reduction in hydrogen. And basically we always see essentially two peaks. Typically the second peak is about 3 times the area of the first peak. And while the first peak produces in a similar temperature range, the second peak is strongly influenced by the type of support that you have present. And in one view, some have suggested that this is due to a 2-step reduction process. I don't know why these arrows are shifted here, but where CO3O4 goes to COO and then COO reduces to the metal, and the second step consumes 3 times as much hydrogen as the first. You can see for the strongly interacting support aluminum, the cobalt oxide species reduce even up to 800 degrees. So when you reduce the catalyst in a reactor, we use a fixed bed reactor at 350, and before transferring to the slurry phase, essentially, if you carry out a TPR after a 10-hour reduction, you can see that there's still quite a lot of cobalt that remains in an unreduced state. So we're not really utilizing our cobalt very effectively. But we wanted to try to understand better these reduction profiles, especially because if you go into the literature, there are several explanations for the reduction peaks for cobalt aluminum. For case 1, I've already talked about, basically goes through COO intermediate. But in case 2, this is a very popular theory, that you have direct reduction of larger CO3O4 crystallites in the first peak, all the way to cobalt metal, and then in the broad peak, you have reduction of isolated cobalt ions, +2 and +3. And then in a third view, this one, by the way, is Arnoldi and New Line, and in this third view, which is Lapidus and co-workers, it's quite similar to the second case. They say that the larger cobalt oxide species reduce in the first peak, but in the second peak, they assign it to reduction of a mixed oxide, shown here. So which one of these is right? Here I've tried to graph each of the different cases. Some of the lettering didn't show very well here. Essentially, in case 2, we have reduction of the isolated cobalt ions in this second broad peak. Whereas in case 1, we have CO3O4 to COO, and then the reduction of COO depends on the interaction with the support. So we sent 6 catalysts to the Advanced Photon Source at Argonne National Lab to test in this new multi-sample holder apparatus, which seats about 6 samples, and they fondly refer to it as a 6-shooter. Basically, in XFs and ZAMEs, we send photons to the sample, and they're absorbed by a central atom. The electron is ejected from the core, and at low energies, we have the ZAMEs, where the photoelectron probes the empty available states above the Fermi level, and that gives electronic information, essentially oxidation state information. At higher energies, the electron has enough kinetic energy to be ejected from the atom, and basically the outgoing wave interacts with its neighbors and is backscattered. And essentially, the backscattered wave interferes with the outgoing wave, and that produces the X-ass effect. And here's a characteristic spectrum showing the Zanes region here, where the electron has just enough energy to reach the empty available states above the Fermi level. And then here we have the X-ass region, where the electron is interacting with the neighbors. So first let's look at Zanes. Here we have Zanes with several reference compounds. For the cobalt metal, it has a very low white line, but in the oxidized cobalt compounds, the oxygen is pulling electrons away from cobalt, and that frees up empty available states, parking spaces for the electron to go to. And so we have much higher white line for these oxidized compounds. And these can serve as a fingerprint along the trajectory of the TPR. So here, after they performed the experiment, which took about a day, they sent me hundreds and hundreds of raw spectra, and then it took about a couple of months to put these together. But here we have cobalt alumina, 15% cobalt alumina. It starts out as CO304, and you can clearly see the transition from CO304 to COO before the metal is formed. And here we have 25% cobalt alumina. And the only difference is this one occurs at slightly lower temperature because of the higher loading. Addition of platinum promoter, you can see that we still have the same transition, CO304 to COO and then the metal. And now it's occurring at much lower temperature. There's a more heavily loaded cobalt catalyst here. So here is unpromoted and platinum. And then for the weakly interacting supported catalyst, cobalt silica and the reference, the COO is formed, but it's a very short-lived intermediate species. And then what we can do is, along the trajectory, we can do a linear combination fitting of the spectra of the catalyst with the reference compounds. And we can see that for every catalyst, we do form 100% COO at some point along the path. Now for X-ass, if you have an isolated atom, you just have an outgoing electron when it's hit with the X-rays. But if the neighbors are present, you have the X-ass effect, where the electron is scattered off of its neighbors. So for a free atom, you have no oscillations. But if the atom is located within a lattice, then it can scatter off the neighbors, and the outgoing wave and backscattered waves interfere. And so there are certain energies here where the absorptivity of the X-rays is modulated. At certain points, the outgoing and backscattered waves interfere constructively, and you have an increase in the absorptivity. At other energies, you have destructive interference, and you have a slight decrease in the absorptivity, and that creates these oscillations. And those oscillations carry information about who is around your atom, how many, and at what distance. Extracting the X-ass signal is a pretty complicated process. It involves pre-edge background subtraction, determination of this edge jump, division by the height of the absorption edge, conversion into K-space. We set up some macro programs to handle a lot of this. And here are the X-ass oscillations in K-space, photoelectron wave vector space. And then after we carry out the Fourier transform, we get one form of the radial distribution function, which tells you who is around your absorber and at what distance, and also how many. So it gives information about, for example, cluster size. Here are the TPR XS spectra essentially confirms the Zane's results. We start off at room temperature, and you can see cobalt-oxygen and cobalt-cobalt coordination in CO304. These three. Then, at a certain temperature, there's a transformation to COO. You can clearly see that. You can see cobalt-cobalt coordination and cobalt-oxygen coordination in COO. And then we form the metal particle. And you see the increase in cobalt-cobalt coordination in the metal. So we carried this out over the 6 samples. And essentially, in agreement with the Zanes, the COO is a short-lived species on CO304 and the weakly interacting cobalt silica. You can see the COO over quite a broad range of temperature here for the unpromoted cobalt aluminum catalyst, and also for the heavier loaded one. And then also for the platinum promoted catalyst, although now you see that everything is shifted to lower temperature. After the TPR, the catalysts were cooled down, and what was observed was that the cobalt silica catalyst had the highest degree of cobalt-cobalt coordination in this first shell. That means that it has the largest cluster size. The catalyst with the strongest interaction, cobalt alumina, ended up having the smallest cluster size. Well, we've carried out other experiments at our lab. We can't always resort to synchrotron techniques to characterize a catalyst. Basically, using this hydrogen TPD pulse reoxidation technique, we obtain the same trends, where we reduce the catalyst, cool in hydrogen, and then perform a sweep with inert gas using a TPD. That counts the number of cobalt active sites, and then we need to reoxidize the catalyst by sending pulses of oxygen to determine the extent of reduction. And when you combine these 2 techniques, you can get an estimate of the true cluster size. So here are the calculations. The TPD sweep goes up here. This is the percent dispersion. That's a fraction of cobalt atoms, metal atoms on the surface. So the TPD sweep gives the number of atoms at the surface. And then in the denominator, we need to have the total number of metal atoms. So that's going to be the total number of atoms in the sample times the extent of reduction. And that comes from the pulse reoxidation experiment. Then using some geometrical relations, you can calculate the cluster size. So for the most weakly interacting supported catalyst, even though it has a high extent of reduction, it has the lowest number of active sites. And that's because the cluster size is very large, as we observed in X-house. For the cobalt alumina catalyst, with low loading, despite its very low extent of reduction, it actually has the highest number of active sites because the cluster size is much smaller. And the cobalt titanium is in between. And so this shows the trade-off in reducibility and cluster size, which ultimately determines your number of active sites. So we wanted to try to promote the reduction of the cobalt alumina and cobalt titanium catalysts. One way is to move to higher loading to try to break the interaction with the support. Other ways to facilitate reduction by adding reduction promoters like platinum, which can dissociate hydrogen at low temperature. Both of those techniques work. Here we have increasing loading effect. We're shifting to lower temperature, and this is the effect of platinum. And platinum, again, facilitates reduction of both steps, as we observed in Zane's and X-house. Cobalt titanium, same effect when we add a ruthenium promoter. And then in chemosorption pulse reoxidation, you can see that adding the metal promoter essentially doubles our extent of reduction while the cluster size remains quite similar. And so we have a doubling of the number of active sites. And that works for a variety of promoters here, ruthenium and rhenium. For increasing loading, we also have an increase in the extent of reduction, but now we have a larger cluster size. And then here we have the effect of both. So this essentially measures the number of active sites here. cobalt silica, you can prepare catalysts with smaller cluster size. If you forego the calcination step and do a direct reduction of the nitrate, you can produce clusters that are smaller. But now, the TPR is broadened, so you start to have reducibility problems. And then if you look at hydrogen chemabsorption pulse reoxidation for the silica catalyst, for calcined, although we have a high extent of reduction, we have a lower number of active sites. This is by the direct nitrate reduction route. The extent of reduction is less, but the cluster size is smaller. And you have a little bit higher number of active sites. Now, how did these lower loading cobalt aluminate catalysts promoted with platinum perform in the reactor? We do have a doubling in CO conversion in our CSTR tests initially, but unfortunately these catalysts deactivate quite rapidly. When you look at the catalysts as close to what's reported for commercial loadings, these catalysts are much more stable, 25% cobalt aluminum. It's shown in the filled symbols here. So we want to try to understand why these catalysts are deactivating. So we pulled out samples during the run and tested those at Brookhaven synchrotron, the National Synchrotron Light Source. And as a function of time on stream in the reactor, we do see increased cobalt-cobalt coordination, which suggests some sintering is taking place. But when you compare Zane's derivative spectra, again, this is electronic state information. This is for the freshly reduced catalyst. This is for the used catalyst. And we do see evidence of a fraction of an oxidized state there that wasn't in the fresh catalyst. And when we look at a number of different reference compounds, cobalt aluminate, addition of cobalt aluminate to cobalt metal and COO gave the best fit. So it seems like we're forming a cobalt support compound. To test the susceptibility of the catalyst to the deactivation by the water, presence of water, which has been reported in the literature, we carried out water co-feeding studies where we basically replace inert gas by increasing amounts of water. For cobalt silica, there's actually a slight positive effect, reported to be a kinetic effect in the literature. Glacia has also observed this, up to a certain fraction, above which the catalyst rapidly deactivates. For titania, with a moderate interaction, we see a slight negative effect at low space velocities where we have the highest partial pressure of water in the reactor, and the catalyst had the highest deactivation rate at that point. But at high space velocities, basically there's a negligible effect. But for cobalt alumina, especially the low-loaded platinum-promoted catalyst, we had a reversible effect of water co-feeding up to about 25%, above which we had a catastrophic deactivation of the catalyst. For the 25% cobalt aluminate catalyst with a larger cluster size, the catalyst was more resilient and more reversible. So we pulled samples out during repeat runs and tested those at the synchrotron. And for the low-loaded platinum-promoted catalyst, we observed at the point of catastrophic deactivation a sharp increase in this feature in the Zanes, which strongly resembles that of cobalt aluminate, which indicates that we probably have cobalt support compounds forming. We didn't see that for the 25% cobalt aluminate catalyst. We did see some indication that some COO had formed at very high water volume levels of added water, but the catalyst recovered when the water was switched off. In XAFs, for the low-loaded platinum-promoted catalyst, we have essentially cobalt-cobalt coordination up to 15% added water, but at 30% added water where we have the catastrophic deactivation, we saw a decrease in cobalt-cobalt coordination and increase in cobalt-oxygen coordination, indicating we formed some kind of oxidized species. But for the 25% cobalt aluminate catalyst, essentially we see only a 25% added water, some decrease in cobalt-cobalt coordination, but when the water was switched off, it recovered. Another interesting finding, and this is the last thing, is for the low-loaded cobalt aluminum catalyst promoted with platinum, we saw a jump in CO2 selectivity when we reached the point of catastrophic deactivation. And I said in an earlier talk given today, cobalt essentially has very little intrinsic water gas shift activity. But oxidized species of cobalt actually do have water gas shift activity, so that again confirms that we have some kind of oxidized species forming. The fact that it doesn't re-reduce when we switch the water off suggests it could be some kind of cobalt aluminate type species, which is quite irreducible. So in conclusion, I want to point out that this TPR Zane's XFs tool carried out at Argonne is a very powerful tool for trying to understand what your TPR means, your conventional TPR. We find that cobalt catalyst reduction proceeds through intermediate COO, and although a smaller cluster size is produced on the more strongly interacting support alumina, the reducibility is much lower. You can facilitate reduction by adding promoters to the catalyst, but there is some sort of a size effect that you really don't want to go to. Those catalysts that deactivated very strongly had clusters of around like 5 to 6 nanometers as measured by our TPV pulse reoxidation tests. And in those catalysts, we observed the formation of cobalt support compounds. More robust catalysts can be prepared by increasing the loadings and overcoming the detrimental impact of water. And those results are consistent with a design above 10 nanometer threshold. And finally, other acknowledgments. My coworkers at CAR, the national labs, Brookhaven and Argonne, some help with the analysis from the University of Oklahoma, and also funding sources, Department of Energy, Fossil Fuels, and Basic Energy Sciences, and also MERCAT and the Commonwealth of Kentucky. If you have any questions, I'd be happy to try to answer those.
So you mentioned that cobalt has water gas shift activity of oxidation.
Yes.
What is the oxidation of cobalt? It's 2 plus or 3 plus.
Which
Oxidized
species?
Yeah.
In that case, we think that we have some sort of cobalt aluminate, some type of cobalt support complex forming, because when we switch the water off, the catalyst does not recover. You still have the cobalt oxygen bonds and the decreased cobalt-cobalt coordination in XFs. And also, that's the case where you see the big jump in CO2 selectivity. And in Zane's, we observe this feature which seems to resemble cobalt aluminate in that case. So for the catalyst where we've reached this catastrophic point of deactivation, that's where we're seeing the high CO2 selectivity at high levels of added water.
Why is so low temperature there, 210?
How so low?
And why so low?
Well,
And why is so low conversion also? I mean, 30%. Why you choose a conversion of why you choose when you decided to work at a conversion of 30% and so a temperature of 210? There is a reason, or?
well, usually we carry out tests at not so high a conversion because therefore you have a lot of high pressure of water. You know, because FT produces water as one of the products.
But you can dilute it also. You can use, for example, I don't know. So, however, okay, your answer is
we are studying the impact of water in this study. So, and the 210 degrees is a typical temperature range for producing the long The longer hydrocarbons?
I know that at 210 you cannot operate industry at 210.
Well, it depends on what you're making.
Huh?
It depends on what you're making. I mean, if you want to make fuels, you're going to operate in one range. If you want to make waxes and heavy hydrocarbons, you're going to want to operate in a different range.
So then you have the effect of other promoters, typically potassium and alkali promoters.
Well, here we're looking at mainly reduction promoters. We're trying to facilitate reduction of the cobalt species interacting with support. We have done some TPR studies where we do have potassium or electronic type promoters, ones that tend to dissociate CO, help cobalt to dissociate CO. In those cases, we see with increasing potassium content that the TPRs are shifted to higher temperatures. So the presence of potassium tends to make your catalyst less reducible.
I have a question.
Yes.
Have you done any tests? Okay, you were looking at, okay, the main focus is the water effect impact on the performance of the catalyst, right?
Yes.
Did you look at the activation rate at standard condition using these catalysts? How do they differ?
Yes. You can sort of see here.
I might have missed it also.
No, actually, I don't have the stability graphs here, do I? Oh, no, I do. Yes, here I have the activation rates, function of percent CO per week. So for these metal promoted, low cobalt loaded catalysts, these catalysts had the highest deactivation rates, unfortunately. But when we went to the higher cobalt loading, the catalyst had a much lower deactivation rate, 1.7% CO per week. That's at one space velocity. This is at another one. Typically, when you go to the lower space velocities, the catalysts tend to deactivate more rapidly because of the higher water pressure.
Okay. Thank you. More questions?
I had one interesting follow-up there. A while, up until fairly recently, I would probably assume the same. But you may have seen there was a recent publication, there was some Dutch people working with Sasol
Right.
that had looked at a commercial bubble column catalyst that looked just like that. It looked like every piece of cobalt catalyst performance data I've ever seen.
Yes.
And they went at least through the Zanes and found absolutely no evidence for oxidation, and in fact reported
Right.
a very significant increase in the extent of reduction of time on stream.
Right.
And I'm having trouble fitting that together with these kind of results.
Yes. Well, they are using a much higher loading of cobalt. Here what we're using is a much lower loading, and we're facilitating the reduction of the more strongly interacting species by using that noble metal. So the cobalt species that we're reducing are probably much less stable than the ones that they are producing with their higher loadings, and they probably have much larger cobalt cluster size than what we have here.
But again, just from a backing up and just looking at the overall perspective, it looks exactly the same if you look at the results. If you showed me a plot of your next plot there,
This one.
that data, any of those,
Right.
and you put that up next to theirs, it would look identical.
Yeah.
I mean, it's,
I-
I'm struggling with how, you always get that same kind of result, but how I can reconcile, in one case, an unambiguous measurement of oxidation and perhaps aluminate formation or titanate, whichever you're working with,
Right.
and then another case that looks basically identical, which they, unequivocally have shown that that's not happening at all.
Right.
And I'm struggling with how to reconcile that the results are still the same on a performance basis.
Yeah, I agree. And there are several people who have looked at oxidation, like Holman's group in Norway and Goodwin's
Right.
group, and they do see a formation of cobalt support compounds with these strongly interacting supports. And Iglesia for cobalt silica has observed the same positive effect that we're getting on the weakly interacting support. So, yes.
I agree.
It's not, the story's not over yet, I think.
Can I put on the question?